What's up, everybody? So today I'm going to talk about special relativity and the consequences of Einstein's special relativity. Now, I'm not going to go into like special relativity, the mathematics, because that you need calculus and tensor physics, and that's a lot of stuff that you would need to build off of. But I'll give you basically the basic rundown of it, and then talk about some consequences that it poses. So Einstein came up with special relativity in 1905, along with 4 other papers. You can check them out. They're called the Annus Mirabilis papers that he published, all in the same year. So special relativity was, and it only works for when space-time is geometrically flat, but yada yada yada. So basically, he came up with 2 postulates. Postulates are basically things that you claim from evidence that allow you to make predictions. So, take a few things and say, if these are all real, then this must happen. So basically, he stated that no matter what reference frame you're in, reference frames are important for relativity. Reference frame is how you're looking at a thing, whether you're standing still and looking at that thing, or whether you're moving and looking at that thing, whether you're looking at it top down, on side, bottom, at the bottom, no matter how you're looking at it, basically the laws of physics are always going to be the same. That's basically the first first postulate, sorry. The second postulate is that the speed of light, speed of light is abbreviated as lowercase c in physics, and it's equal to about, and I know this off the top of my head, 299,792,458 meters per second square. So take that. That's obviously that nothing can go faster than the speed of light, and the speed of light, no matter what, always goes at that speed, light, or at least light in the sense of a photon, which is just a particle of light. So basically, light can only go at that speed. Now, this causes some consequences, but now this you have to go into Lorentz transformations and stuff like that, which is sometimes I don't even really get it. Sometimes it's really complicated, but I can explain some of the consequences of it pretty easily, as long as you sort of have a common sense and an idea of the world around you. The first one I'd like to talk about is simultaneity of relativity. Now, the idea is that because of relativity, actions that may seem simultaneous, happening at the same time, might not appear to be happening at the same time. For instance, say you are standing still, and far off in the distance, you see 2 lightning bolts strike about 100 meters apart from each other. And this is the thought experiment Einstein designed to prove this. Now, so basically, you see them and they strike at the same time. Now imagine you're on a train and you're moving side by side, though, where the lightning bolts will hit, and you're moving toward one of them and away from the other. Now, if the lightning bolts strike, they won't seem simultaneous, since light moves at a constant rate. The light that's traveling to the one you're moving towards, you'll hit it. You'll see the light of the one you're moving towards before you see the light of the one you're moving away from, just because of you're moving towards it and it's moving towards you, versus you're moving away from something and it's moving towards you, which kind of makes a little bit of sense. Now, second thing is called it's the absolute speed limit. Obviously, you probably always hear light's the absolute speed limit, it's the cosmic speed limit, yada yada. What does that mean? Basically, what it means is that light is the fastest something can go in the universe. And the reason for this is called relativistic mass and speed limit principle. So basically the idea is that as you move faster, and this only gets really appears once you get to about like 25 to like 50% the speed of light, which basically nothing gets to in like everyday life. Like, you can't run that fast, obviously, but the idea is that as something goes closer to the speed of light, as it gains more speed, it gains mass. Now, mass is not weight. Don't get those two mixed up. Weight is how mass interacts with the gravitational force of a body. For instance, because weight down here on Earth is just, it would be different than your weight on Mars. Your mass would stay the same no matter what. That's just the amount of matter you have in you, or but more specifically, it's actually technically the amount of inertia it would take to move an object. But those are basically similar concepts, so people just say either one. But basically, what we were talking. Oh yeah, that's it. Relativistic mass is mass that is gained or appears to be gained as you move closer to the speed of light. Now, the reason you can't get to the speed of light is that as you get closer and closer and closer to the speed of light, if you have mass, you will gain relativistic mass, meaning that you can never get to that speed because you're being weighed down by all that mass. And when I mean weighed down, I mean getting slowed down because you have so much mass. And the mass starts to reach infinity, which, can't go any faster, really. This doesn't work, however, for photons, which are particles of light, since they do not have mass. And since they don't have mass, there's no mass to gain. So they sort of are independent of that. And he also showed that light is the fastest thing, or light stops. If you move at the speed of light, time stops. Now, the idea with this is kind of, just think of this in your head. One, say you have a clock, just in front of you, and you move away from it at the speed of light. Since light is the fastest thing, the clock won't appear to change, since the light that is hitting your eye from the clock is always going to be the same light if you're moving away from it at the speed of light. Yeah, take a shot every time I say light, honestly. Anywho, so basically, since the light's moving away, and you're moving away at that same speed, the clock will not appear to change because it's sort of frozen in time, as if. Not really, but from your perspective, from your viewpoint, your view frame, Anywho, last two actually things I wanted. Lastly, the first is time dilation. Basically, as you approach this speed of light, so this is another thing with special relativity. Time always appears the same for you, no matter what. So time. Sorry about that. Time will always move normally for you, no matter what. No matter whether you're going at 0% the speed of light to 50 to 99.99999% the speed of light, you will always feel like time is moving the same for you in your reference frame. However, that's not true for everybody else. For instance, say if I go up in a spaceship, move at 50% the speed of light. Like say I take off right now, I go up spaceship, go off, move at like 50, say 40% the speed of light for 5 years. I come back, you guys would all be like 60 years old, even though I would only be about, only have aged 5 years, because for my reference frame, I've only been up there for 5 years. You guys would all be 60 years old or such, because for you, time is still moving normally, but for me, time is also still moving normally. So the consequence is that your time is moving just much faster relative to mine. Now, finally, the last thing I was going to talk about is length contraction. Now, the thing with length contraction is it's kind of complicated, but as long as you remember that light has to always travel at c, that speed, it doesn't really, it boggles the mind, but it makes sort of a little bit of sense. Now, the idea for this is that if you're moving very close to the speed of light, like super fast, close to the speed of light, what happens is that you will see objects, their lengths will appear to shrink, because to keep up with that, your speed, light always has to be moving at the same length every, so however many units of time, whether that be seconds, minutes, hours, yada, yada, yada. So the length will have to contract to compensate for that if you're moving closer to the speed of light. And as you get to basically the speed of light, lengths will become negligible. For instance, if you moved at 99.999999999999999% the speed of light towards Earth, Earth would appear to quite literally be flat, or at least as thick, basically as thick as, on say like, or as basically as tall. How do I explain? As thick, yeah, as basically my body standing up right here. Like it would only be this long in the direction you're traveling. So, to a cosmic light particle, the Earth is flat debate makes sense. However, it is not true, obviously. In a reference frame similar to ours, where we are traveling basically no 0% the speed of light. So those are just the things I thought were very interesting, that you could sort of comprehend without understanding the Lorentz transformations really in-depthly or such, and sort of can just think about in your mind. But yeah, so I thought that was cool. See ya.